So from last two videos, we saw that the space for each irreducible representation we associate with this E pi, this matrix coefficient, they span a space inside the L2 of G. And from last time, the Schur orthogonality tells us this each of these E pi, this is going to be a finite dimensional space with a orthonormal basis, and we know its dimension is going to be d pi squared because it's spanned by d pi square number of orthonormal vectors. All right, so and if you think about what happens on this E pi, we saw this E pi is invariant for the left regular representation. So if I restrict my pi, this lambda, left regular representation on this E pi, then I get a finite dimensional one. So in this video, we're just going to study what it is, okay? I'm going to show that it's actually related to the representation pi. It's basically a multiple of the conjugate of this pi. So for that, I need to give a definition. So I say I conjugate. So if let pi going from G to some bounded linear operator on H pi, let's say it's irreducible, or it doesn't really have to be irreducible. It has to be finite dimensional. If I let the following representation is let pi bar of x, okay, so this is essentially just equals to the pi x inverse, and then I do the matrix transpose, okay, so you don't do the conjugate transpose, you just do the matrix transpose. And this is essentially just if you think about this pi x, if you fix a certain orthonormal basis, you do the pi x, this whole matrix, you conjugate that, okay? So this is going to be a representation again, okay, because essentially just if you think about this pi x as a matrix, as a d pi by d pi matrix, you're just taking the conjugate, so that's clearly going to be a finite dimensional representation, okay? And this one is certainly also irreducible, okay? So this pi bar is also irreducible unitary representation, okay? That's quite clear. And this pi bar, most of the time, is not going to be unitarily equivalent to pi, in fact, okay? There may be totally different representations. But I want to prove the following proposition. So if you consider the left regular representation, lambda, and you restrict it to this invariant subspace, so this E pi, so here pi is a irreducible representation. And well, we know this E pi is invariant for lambda, so the restriction is going to give me a finite dimensional representation. So this one actually just going to be unitarily equivalent to a bunch of pi bar. Okay, it's going to be actually exactly d pi copies of these pi bar. Okay, so they're going to be unitarily equivalent to a bunch of pi bar. So this by d pi times that, I mean basically d pi copies of direct sum. Okay, so you have d pi copies of them. All right, so to prove this, okay, this is actually just a consequence of the Schur orthogonality. So let's fix an orthonormal basis. Let's say fix E1 up to E of d pi, orthonormal basis for these H pi. And once I fix the orthonormal basis, I can talk about this orthonormal basis for the E pi. So let's let I have the square root of this d pi times the pi ij. That's going to be an orthonormal basis for the E pi, okay? So this is a d pi square dimensional finite vector space. All right, so let's consider the following thing. So if I let aj, that's going to be a unitary, so I want to map it from the H pi to a subspace of the E pi spanned by the following. So I spanned by I fixed the second coordinate, basically I fixed the column to be j, so I do the square root of d pi of pi ij here. I is from 1 to d pi. So this is essentially fix the jth column of these pi ij's, okay? You consider the linear subspace. This is aj is going to map the ei, this is also known this basic vector ei, to the d pi times pi ij, okay? So it maps an orthonormal basis to an orthonormal basis. Of course, on the right-hand side, it's only a subspace of e pi, all right? But you can see the right-hand side is still a d pi dimensional, so this aj is going to be unitary from its domains to its range. Okay, so this is unitary. Okay, because it maps orthonormal basis to orthonormal basis. And let's just consider how does lambda g act on the range of these aj. So if I consider lambda g, basically left regular representation, apply to say aj on ei. So this is essentially by definition, I have the square root of d pi. You have the lambda g applied to the pi ij. Okay. So how does left regular representation or left translation apply to pi ij? So let's do some calculation. So lambda g, when you apply to pi ij of x, so this is left translate. So you do the pi ij of the g inverse of x. Okay, so you left translate by x. And what you do is that, well, you think about this pi ij as a matrix, the ijth entry. So this is essentially pi of the gix. You can think about the ij entry is the pi ij of the g inverse x. Okay. And because the pi is a unitary representation, so this one is going to be equal to the pi inverse, pi of g inverse multiplied by pi x. And they are basically two n by n matrix. You multiply them together, you try to find the ijth entry. And this is not hard to see. So this is essentially you do let's introduce a new index, the k going from 1 to d pi. So you look at the pi of g inverse, but you look at the ik entry, and then you multiply the corresponding one in the second matrix, which is on the kjth entry of the pi of x. Okay, so you do this summation. And one thing you see is the following. So because you have this pi bar of these x, is essentially just equals to the pi of x inverse and the whole thing transpose. Okay, or let's maybe move the transpose to the other side. So the pi ij ik entry of the g inverse is essentially just the ki entry of the pi bar. Okay, so you immediately have this pi of ik of x inverse that's going to be equals to the pi bar. If you think about it as a n by n matrix or d pi by d pi matrix, that's the ki entry because that's the transpose of the x. Okay, so this I can rewrite this as summation k going from 1 to d pi. The first entry becomes the pi bar evaluated at ki of x, g, and then you have a pi of kj of x. Okay. Well, pi of kj of x, that's essentially just the range of this aj. Okay, you can. So let me just write it this way. So this one really what it looks like is the aj of the kth basic vector ek. Okay, this pi bar ki is just a scalar. Okay, so I can rewrite this as so I can move the aj because it's a linear operator. So this is the aj applied to this vector k going from 1 to d pi of the pi bar ki evaluated on g, and then I multiply the kth unit vector. Okay. So what exactly is the pi bar? Well, pi bar of ki, so by definition, this is going to be equals to the inner product of this pi bar ki of g evaluate. So first of all, you inner product, you multiply on ei, and then you inner product with ek, and then you apply ek again. So you let k going from 1 to d pi. Okay. And if you look closely enough, okay, so this summation, this is essentially just equals to the pi bar of g applied to the ei. Okay, so this is some basic matrix theory. Okay, you think about how the matrix works. Okay, this pi bar, you have this, if you just multiply by the ei, basically you take out the ei column. Okay, and the ei column you can rewrite it as the ki entry multiplied by the kth basic vector. Okay, so this is essentially just pi bar g applied to ei. Okay, so let's see what we end up with. So we started with lambda g pi ij, which is essentially just lambda g applied to, oops. So I have the lambda g applied to the aj of the ith basic vector. So that's the same as the aj of the pi bar of g applied to the ith basic vector. Because they agree on all the basic vectors, so let's just pretend this ei doesn't exist there. Okay, so these two operators, they have to be the same. Okay, where we tested it on all the orthonormal basis, so these two operators has to be the same. Okay, so in other words, this lambda g is just going to be equals to aj pi bar of g and then aj star. Okay, so essentially your lambda restricted to the range of this aj. Okay, that's going to be going to be unitarily equivalent to this pi bar. Okay, and you know the range of this aj is spanned by the jth column, and you have d pi of them altogether. All right, so if you take the direct sum of all these ranges of this aj, let's say going from 1 to d pi, then you get the entire e pi. Okay, so that just tells you if you restrict to this e pi, so this e pi spanned by a bunch of these column spaces, you have d pi copies of them, that's going to be unitarily equivalent to d pi copies of pi bar. Okay. So just a short exercise. So if you actually run the same argument for the right regular representation, things are actually a lot easier. So if you do the right regular representation, let's call it rho, and then you restrict to pi, that's actually also unitarily equivalent to d pi copies, but you actually just need a pi. Okay, so I'll leave that as an exercise. It's essentially the same proof. All right, so basically now we have a really good description of how the pi looks like, how the lambda looks like, the left regular representation looks like on each of these e pi. Okay,